notice that in these problems, we still looked at the graph to figure out what these individual limits were when we broke it down into products of limits or sums of limits. So this next group actually find those individual limits that we couldn't figure out unless we looked at the graph. So I'm just listed the next 6 laws here. So that first one is the power law. And this tells us that if we have a function raised to an integer power, and we're taking the limit of that, we can actually find the limit, bring the limit inside the exponent. So we can evaluate the limit of just f of x and then raise that limit to the nth power. And this is derived by repeatedly applying the product law. So that law is telling me that I can bring this limit symbol inside this power, right? So I have this. So I can find the limit of this expression inside this power. So I can apply the sum law that we just saw. So what's inside here is equal to the limit as x approaches 2 of x plus the limit as x approaches 2 of 1. But now we're going to look at 2 other laws that will help us definitively say what these are. So looking at graphs, we've kind of pretty intuitively figured out what they are, but this law is going to firm it up for us. So we're going to look at 2 more laws before we answer this, and we'll be back to this problem in a minute. So the first one we need to look at involves a limit of the constant function. So I'm going to flip back to my last problem. Notice that I have the limit as x approaches 2 of 1. 1 is just the constant function, right? So that's what we're going to use. This law is what we're going to use to help find that. So the limit of a constant function is just that constant, which makes sense because the y value is never changing for a constant function. It's always the same. It doesn't really matter what the x value is. The y value, in this case, when the f of x equals 4, it doesn't matter what x is. Y is always 4. So that makes sense that the limit of a constant function is just that constant function. So I'm changing my horizontal line here, and it doesn't matter what my x value is, right? The y value is always the same. So that tells me that the limit is always just c, the constant. The next law is going to help us figure out the first part of this problem. So the limit as x approaches 2 of x. Remember that y equals x is called the identity line. If we look at the graph, y equals x always. So if x is approaching any number a, and y equals x, then y is approaching that number as well. So this law helps us answer that second part of our problem from before. The limit as x approaches 2 of x. Well, that's going to tell us that that limit should be 2. So let's go back to that. Now we can finish that example. So we'd gotten to this point. The limit as x approaches 2 of x plus 1 to the 4th. So applying that constant function law tells us this limit's going to be 2. And applying the identity function law tells us this limit's going to be 2. And applying the constant function law tells us this limit's going to be 1. So we're going to end up with 2 plus 1 in those brackets raised to the 4th power, or 3 to the 4th, which is 81. So the next law tells us that the limit as x approaches a of x to the n is just a to the n. And that we can derive by using that power limit law that we saw in law 6, I believe it was, with the identity function f of x equals x. So looking at examples always a little bit better. So the limit as x approaches 2 of x cubed, this is just telling me that I can take the limit as x approaches 2 of x, which we saw by the identity function law is just 2, and then raise that to the 3rd power. So my answer is going to be 8. The last 2 laws are limits of nth roots. So again, we are pulling those limits inside the radical and evaluating those limits inside the radical and then taking the radical. Evaluate this limit, x to the fourth plus 3x minus 5 as x approaches 1. If you're asked to evaluate a limit and to justify each step, this is what you would do. You'd say, well, I'm going to first apply the sum and difference law and break it up into the limit of the sums or differences. Then I'm going to look at each limit, and this first limit, I can apply that power law that said I can just replace x with 1. So I'm going to apply the constant multiple law, so I can pull out that 3. And then I'm going to apply the identity function law and say that this inside limit's just 1. And then for this last term, this is a constant function, and the limit is just that constant. So putting it all together, I'm going to add 1 plus 3 minus 5 to get minus 1. And we can verify that graphically. Here's another example. Now it's a rational function. So since my limit is x approaching minus 3, and minus 3 is a 0 of this denominator, we can't use the quotient law yet. So first we have to do some algebra, and that is a big part of these limit problems. You're going to have to do a lot of preliminary algebra a lot of times to get to the limit. So we factor the numerator and denominator, and notice we have a common factor of x plus 3. So that means that x equals minus 3 as a whole. So we can cancel those and we get this simplified function. So the values of this function all around x equals minus 3 are the same as the values of this function around x minus 3, right? All the other function values are the same between these two. So that means I can find the limit of this simplified function, and it's going to equal the limit of this original rational function. So let's look at that limit. Now I can use the quotient rule, the quotient limit law. So I can take the limit of the numerator and the limit of the denominator on that simplified function. And again, using the identity function law in the numerator and the sum or difference law in the denominator, and then again the identity function law and the constant function law, and I get 3/7.